Section 5 shall cover regression and correlation. So let's move on. Regression. Simple linear regression is a statistical method that allows us to summarize and study relationships between two continuous quantitative variables. One variable denoted as x is regarded as the independent variable. The other variable denoted as y is regarded as the dependent variable. The regression line is the best fitting line that can be drawn through the point on a scatter plot. So this will be your y-axis and this one will be your x-axis. So this is the independent variable, the dependent variable. As you can see, the blue dots are the points on the scatter plot. So you can see these points are just jumbled around this area, but we need to represent it in a form of relationship. So that's what the regression line is used for. So it gives the best fitting line, which means it draws a line where the points are evenly divided between the two halves, this side and this side. So it finds the best fitting line. So this one is called the regression line equation, and this is the regression line. So let's move on. The overall idea of the regression is to examine two things. Does a set of independent variables do a good job in predicting a dependent variable? 2. Which variables in particular are significant predictors of the dependent variable, and in what way do they, in terms of magnitude and impact? So the purpose of the regression regression line, this topic, is mainly to find the relationship between the independent and dependent variable, and if the relationship exists, to what extent in terms of magnitude and impact. The regression line equation is represented by this formula: y, your dependent variable, x, your independent variable, and a is the y-intercept, and b is the gradient of the regression line. So let's say you've got the y-axis, this is your x-axis, and so now this is where the value where your equation passes through the y-axis. So this will be your a, and b is the gradient on the line. Gradient is this distance up, which is your change in y. This is your change in x. Distance from here to there. So this is your gradient. So this is your equation of the. So in this section, in order for you to determine your b, you must know that your b is equal to the standard deviation of x and y, and s is the variance of x. So remember, s squared is equal to variance, and s is equal to standard deviation. So you can say SD, standard deviation. So you must know, when you see this one, an s squared, it means it's the variance of x, but this one is the standard deviation of the covariance of x and y. So what we mean, covariance is like the variance when you combine x and y. So s squared xy is the covariance, but in this case we only need the standard deviation of xy over the variance of x. So, but we know that standard deviation of xy is equal to this formula: summation of xy minus the summation of x times summation of y over n, all over x minus n minus 1. Then the variance of x is equal to summation of x squared minus, in brackets, summation of x squared over n all over n minus 1. And for you to determine your a, use this formula, y bar, which means the mean of y minus b, mean of x. So how these points come about, we know that this line, it passes through x bar. So we are saying there's a point along the line where in which x bar and y bar passes through. So this is like a point on your coordinate on this Cartesian plane. So we are saying the midpoint of all the points on the scatter plot is the midmost point in the scatter, which is represented by this coordinate, which passes through the regression line. So we know that if x bar and y bar passes through this line, which means we can substitute their values in order to determine a. That's why if we know your y bar and you know your b from this formula, then you also know your x bar, then you are able to calculate your a. So let's move on to an example so that we can illustrate how this works out. So an example, determine the regression line of the following data. So this is your x data and this is your y data. So remember, you have got your formulas. So you need to first calculate your b, then you calculate your a, then when you get your a, remember your equation is y, your regression line is y, this goes to a plus bx. So once you get your b, a and your b, you'll be able to determine your equation of the regression line. So let's work it out. So the first step of the solution, remember this was given on the question. So the first step, you add the columns so that you get the total. You add these columns. If you add the columns, you're supposed to get to 195. So this will be your summation of x. And you should sum also these ones, get your summation of y. Then the other part is x squared. So the x squared is your squaring these figures there. So 0 squared is 0, 6 squared is 36, 0 squared is 0, 12 squared is 144. Then you continue with your expression. So once you find the squares of x, then you sum them up in this column. When you sum them up, you get 2747, which is your summation of x squared. So the fourth column is your product of yx. So it's y times x. So it means they are multiplying x, x times y in order for you to get this one. So you are multiplying these two x times y in order to get this one. So 0 times 6 is 0, 6 times 9 is 54, 0 times 14 is 0, 12 times 22 is 168, 164, 264, forgive me for that. Then once you do all the xy products, then you get all these figures. Once you get those figures, you sum them up to get 8,820. So this is your summation of xy. So once you are done with that, you proceed to the next stage. So let's go on. So you know that if you count your numbers from your data set given in your equation, you know that there are 15 data sets. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So your n is 15. That's why we wrote here your n is 15. These ones we have them from the previous table. Then for you to get your x bar. Remember x bar from the previous sections, we said x bar is summation of x divided by number of items. So summation of x, it's this one, 195 divided by 13, 15, then you get your 13. Then you do the same for y, summation, y bar is also summation of y over n, which gives you your y is 556 over 15. If you simplify it, I'm supposed to get the 7.067. So once you get all these figures, it means you're able to calculate your xy, which is given by this formula. Then you input, remember your summation of xy is this one, which gives this figure. Then your summation of x and the summation of y, the summation of x, summation of y, which are represented by this and this. So you can see. Then your n is number of items in the set, which is 15 in this figure. Then your n minus 1, 15 minus 1, because your n is equal to 15. Once you simplify it, you're supposed to get 113.71. Then your variance of x is given by this formula. You know that your summation of x squared is this one, 3,747, which is written by this one. Then this one is your summation of x. Summation of x is this one, 195. But you say 195 squared to get this one. Then your n is 15. And this n minus 1 is 15 minus 1. When you simplify it, it's supposed to get this one, 86.571. Then, so therefore your b is equal to s xy divided by variance of x. So you just say this one divided by this one. Then you get this one. So when you simplify it, your b is equal to 1.34. But we know that our a is equal to y bar minus b x bar, which is equal to your y bar, we've determined it here. Then your x bar, we've determined here, 18. Then your b is this one. So you just input these figures, get this equation, and just simplify it, supposed to get 19.985. So once you do that, hence your regression line equation is equal to y is equal to 19.985 plus 1.314x. But I think it would be good to simplify it to two decimal places. So y is equal to 19.99 plus 1.31x. So you can simplify to two decimal places. I think that's fine. So that's all you have to do in your regression. So let's recap. Determine the regression line of the following data. So you've got your x data and your y data. Then the first step is to draw this table. Once you draw this table, make sure the first column is xy, and the other one is x squared, the other one is yx. So you input your figures, then you find the totals, then you x squared, you just square this column. Once you finish squaring each item, then you sum it. Then you do your xy, which means x times y, then you get these figures. Then once you do that, you sum them up. Once you do that, it means you've determined these symbols, x. Once you do that, you can also determine your x bar and your y bar. and you can proceed to input these figures and these symbols given here. Then you simplify it. Once you get your B, you are able to input your B because you already have calculated X bar and Y bar, so that you can get your A. Once you get your A, then you input your values of from the equation. You know that your general equation is the regression line. These formulas are also given in your exam formula sheets. So, but once you work a lot of problems, you'll be knowing them by head. So let's move on. Correlation. Correlation. The product moment correlation coefficient, also known as the Pearson correlation coefficient, denoted by R, is calculated on the basis of how the points lie from the best fit regression line. So correlation it's mainly a measure of a relationship. So you can see R is determined by this formula, and it's also given in your exam datasheet formulas. But I have just simplified it because this expression is also equal to another bigger expression. But just for simplicity's sake, I just included it. But if you want to see the full formula, you can check it out in your exam datasheet or in your relevant textbook. So, but product moment correlation coefficient, also known as Pearson correlation coefficient, denoted by R. So this is the symbol for the correlation coefficient. Is calculated on the basis of how the points lie from the line base of it. So basically, when you have your points, so let's say you draw your baseline of it, means there are several points scattered around this regression line. So correlation, it measures how far away are the points from the line of base fit or the regression line. So if the points are far away, it means there is a weak relationship. If they are closer, it means there is a strong relationship. So generally, that's how you should know it. So interpretation of R. So R, remember, it ranges from, it's a range from -1 to +1. So positive correlation is like this. A negative correlation, it's like this. So positive correlation, it means as X increases, Y also increases. Negative correlation, it means as X increases, Y decreases. But basically, this is how we interpret. So when R is less than 0.2, we say there's a slight correlation and almost no relationship. So this applies for the positive and negative, but so if it's in the positive, it means there's a slight positive correlation. If it's negative, it means there's a slight negative correlation. So, but in this case, we are just using the positive one, but you know that it also applies on the negative one. So from 0.2 to 0.4, you know that there's a low correlation. So we are basically saying when R coefficient correlation is close to 0.2 or any number between 0.2 and 0.4, you know that there is a low correlation. There is a definite but small relationship. From 0.4 to 0.7, it's a moderate correlation, but there is a substantial relationship. From 0.7 to 0.9, it's a high correlation, meaning that there is a strong relationship. From 0.9 to 1.0, it's very high correlation, very dependable relationship. So it means as the numbers are closer, from 0, it means there is no relationship. 1, there is a perfect relationship. So the range here is R increases, the correlation increases. So that's how we interpret this. So sometimes in some exam questions, you will be asked to calculate the correlation coefficient. Then when you get the value, you are asked to interpret. So these are the ideas of how you can interpret depending on the given data set. So let's move on. Things to note. Correlation is not a robust measure. That is, it is strongly affected by outliers. So it means, let's say, if there are maybe there are points which are along this regression line, but they are outliers. So remember, correlation, it measures how far away are the other points from the regression line. So if they are outliers, it means they are far away from the regression line, which can end up affecting the correlation figure. So outliers, they affect correlation. So not that correlation is not a robust measure. Correlations can be misleading if the underlying population aren't homogeneous. Therefore, researchers should ensure that subgroups in a sample do not differ markedly on either of the more correlated variables. So when you're saying homogeneous, they must be of the same kind. They're of the same breed. So if you just do your samples without making sure that they're homogeneous, your correlations may be very misleading. Correlation are sensitive to restrictions in the range of variables. Therefore, researchers should make sure that the correlated variables do not have unrepresentatively small variances. So if you don't choose your samples carefully, you might end up having small variances between your data inputs, which can affect the correlation. Because if there are small variances, it can mean a high correlation. Just as we acknowledge that sample means are only estimates of population means, and we exhibit random sampling variation, so we must acknowledge that sample correlation coefficients are only estimates of the population coefficient, and we also exhibit sampling variation. What basically it means, if you have South Africa as your population, and we take Pretoria as your sample, so if we do a sample correlation, just know that it's an estimate of the total population. So we are just saying just a sample means are only estimate of population means, and we exhibit random sampling variation. What it basically means is, like, if you take another sample, maybe from Joburg, the results might be slightly different from those from Pretoria. So just know that sample correlation coefficients are only estimate of the population correlation coefficient, and we also exhibit sampling variation. Things to note continued. Correlations are meaningless if the variables are not related in a linear manner. So correlations, they work for linear relationships. A lack of correlation between two measures does not imply lack of association between them if they are non-linearly related. So if correlation is R is equal to 0, it means there is no linear relationship, but it doesn't mean there is no association. So the relationship might be a bell-shaped one, like when x increases, y increases to a certain point, then it starts to decrease. As x increases, y starts to decrease. So lack of correlation just means that there is no linear relationship, but the two or the variables might be associated in a different manner. So a lack of correlation between two measures doesn't imply lack of association between them if they are non-linearly related. Because of the possibility of such non-linear relationship, you should always inspect scatter plots of your data rather than simply relying on correlation coefficients. So it means if you see that there is no correlation, you should also just check your data scatter plot to ensure that if there is no other relationship which is not linear. Last thing, a correlation of 0.8 doesn't represent an association that is twice as strong as a correlation of 0.4. The correct procedure to compare correlation coefficients is to calculate the square of each of the correlation coefficients, which is R squared. R squared is known as the coefficient of determination. So if you want to compare two correlation coefficients, you must calculate the coefficient of determination, which means you say R squared is equal to 0.8 squared is equal to 0.64%. So R squared for 0.4 squared is equal to 0.16, which is 16%. So in other words, if you are comparing coefficient, which means here it's like 4 times. But if you just compare it as a raw correlation coefficient, you get the wrong representation of the how strong each of them is. So it means 0.8 correlation of R is equal to 8 is 4 times as strong as correlation of 0.4. So these things that you should note. Thank you for watching. If you have any questions concerning this section or you need any further information, call us now on 074-920-9697. Have a great day and see you in the next chapter.